Okay, so as usual we're starting out here with a little bit of atomic structure, and we've got to find tin in your periodic table, and it's there down towards the bottom of group 4. And remember that the key number you want at this point is the number at the bottom of the square, which is 50, because that's the atomic number, and that tells you how many protons there are in the atom. That's the definition. But so long as we're talking about atoms, it's also the number of electrons. So straight away you can fill those two in: 50 protons, 50 electrons. To get the number of neutrons, we have to work with this 118 number, and that, remember, is protons plus neutrons. That's the mass number, which is the sum of those particles in the nucleus, so the protons plus the neutrons. So if we take 50 away from that, we get 68, and that's the number of neutrons. Okay, so 50 away from 118, 68 is the number of neutrons. Then it says, what about if we have tin 120 instead of tin 118? And clearly the mass number is 2 more, and remember it's the number of neutrons that's different. If the protons were different, it would be a different element, so it's not that. It has to be the number of neutrons that are different, and again, be specific. You have to say 2 more neutrons in tin 120. Okay, next bit, usual definitions. Lots of marks. As you can see, 3 marks for relative atomic mass, so make sure you get them right. So it's the average mass of an atom of an element on a scale where an atom of carbon-12 has a mass of 12. Make sure you get it word for word. Don't let yourself get away with getting it nearly right, because that's what gets you 1 out of 3, 2 out of 3. That's what you really don't want. Okay, so average mass of an atom of an element on a scale where an atom of carbon-12 has a mass of 12. Okay, now we get to the first of the calculations in this paper, and we've got to calculate not just the number of moles, but the actual number of tin atoms in this bronze shield. So the starting point is 2.08 kilograms. You have to be able to convert that into grams, because remember, grams are what you can then convert into moles, and that's the key to everything else in chemical calculations. So you have to know that a kilogram is 1,000 grams. So if you didn't know that, that's something that's important to take on board. If you get other bigger units like tons, they usually tell you how many grams it is. But kilograms, they expect you to know, is 1,000 grams. So you have to multiply that by 1,000 to get 2080 grams. And then you have to remember the relationship that moles equals mass over mR, which is 2080 grams divided by, well, in this case it's the AR rather than the MR, because we're just talking about a metallic element, and it's even given you the number to save you looking it up, 118.7. So you calculate that number and you get 17.52 moles is the answer to the first bit. And then you've got to convert that into the number of tin atoms, and what you have to remember is that each mole contains Avogadro's number of atoms. So you've simply got to multiply that number by Avogadro's number. So the relationship you want is that the number of atoms, or it could be molecules or whatever particles you want, so we'll just put number of particles is equal to moles times Avogadro's number. Okay, and you need to learn that one along with all your other mole calculations. You know, it's not a formula you use so often, but it is an important one. So we've got to multiply 17.52, and Avogadro's number, remember, is on your data sheet. If you look on the back of the periodic table, it gives you the value of that. So that's equal to 17.52 times 6.02 times 10 to the 23, and that comes out to be 1.05 times 10 to the 25. Okay, make sure you don't overround. It's not just 1 times 10 to the 25. You need those 3 significant figures in there. 1.05 times 10 to the 25, because it says give your answer to 3 significant figures. Make sure you don't miss those little instructions. It's really important, if it tells you to round it to a specific level, that you do that. Okay, part D, again, is a calculation, and again it's a very standard one. The empirical formula is a method that you absolutely need to learn. So the slight trick in this one is that it gives you the percentage of tin by mass in a tin oxide. It doesn't actually tell you what the percentage of oxygen is, but obviously because you've only got tin and oxygen in the compound, the percentages have to add up to 100, so the percentage of oxygen is just 100 minus 78.8. So we can set up our little table as you do. Put your elements across the top, copy down. Remember, it could be just masses in grams, or it could be percentage masses. It doesn't matter. You just put them in here. So 78.8 for the tin. For the oxygen, you've got to take that away from 100. So you get 21.2. And then remember the recipe. First of all, you have to divide each of those by the relative atomic mass of the element. So for tin, you divide it by 118.7, which gives you 0.664. And for oxygen, you divide it by 16, which gives you 1.325. Don't round much, if at all, at that point, because if you round these numbers too much, they end up not giving you whole multiples when you get to the calculation. So leave the rounding till the end. And then you divide by the smallest of the numbers that you come out with, which is obviously that one. And now when you divide through, that one is more or less double that one, so you get 1 and 2. And remember to then write down what that tells you. If you just leave it at that, you just get 1 mark out of 2. But you have to write, so the empirical formula is, and fill it on the line, SnO2. And that's the end of the question.